Hey,
Asas.
Asas.
Angelo here.
Ethan here.
How do you walk? I mean, walking is an everyday thing. You just place yourself in one foot in front of the other, and just using your own momentum, you just propel yourself forward. Using momentum.
Whenever you feel that you want to achieve something, you would say that you are
Gaining momentum. But what is momentum?
In physics, momentum is defined as a quantity where mass and velocity are multiplied together. But I mean, what does that truly mean? We're having two fundamental quantities and mashing it together, and scientists call it a new variable. Beats me. Anyone can do that, right? Wrong! Momentum derives from the word mover, originating from Latin, which means to move. If I move because I have mass, I also have momentum. Now the question that arises is, what can we do with a mass in motion? Newton's cradle. Its origins are iffy, with actor Simon Pebble coining the name for the sake of making toys. But it goes to show the relationship of momentum. If I take one ball and let it drop, notice how only the ball on the opposite side rises relatively at the same height as the other. Again, let's take another scenario and take two balls. The same thing happens like a reflection, a mirror. The same goes for three balls and even four. Something is remaining constant here. Let's say we have two balls, and I decided to throw them against each other. Both masses are known, but only velocity of one of the balls are known, with the other velocity unknown before the collision. If we know the immediate velocities after the collision, how would we solve the unknown velocity?
In Newton's cradle, in our scenario, we can use the conservation of momentum. The sum of all the momentums before the collision is equal to the sum of all the momentums after the collision. Naturally, with this, we can form a relationship connecting two or more objects in a collision based on only these two variables. However, something is missing. Note that in Newton's cradle, the speed of each collision is ever so slightly decreasing, even though the mass is still the same. Does that mean that the conservation of momentum is not conserved in each and every scenario? No, not exactly. For that, if we want to look at the gigantic picture of momentum, we would have to look at two types of collisions. These two collisions are what we call elastic and inelastic. But these two categories aren't really a cookie-cutter explanation for all collisions. Most collisions in the world are mostly in between, but generally speaking, the majority of collisions are inelastic in some way. But we have this major disclaimer about this. In the real world, we have resistive forces, and examples of it are friction and air resistance, which makes idealistic collisions a little bit of a problem. So in our idealistic world and in your physics problems, the only thing in our scenario for these collisions is the amount of blocks that you plan to collide. But in short, we are only isolating the system. Now we can go and explain the varieties of each and every type.
Let's take a closer look at the elastic type and what makes it so special. If me and Angelo were to run at full speed, we would both collide and then bounce off of each other. This can also be applied to if I were to throw a ball into a wall. No matter how you look at it, two objects are colliding with one another and immediately bouncing off.
There you go.
As you can see, it's hitting the floor a bunch of times.
You're correct.
Looking at it from a mathematical perspective, both objects, mass 1 and mass 2, are coming towards one another with different velocities, v1 and v2. We can derive these variables into a typical momentum equation, that being m1 times v1 plus m2 times v2 is equal to m1 v1 prime plus m2 v2 prime. In the equation, we notice that the masses of both objects always remain constant, but the key changing factor is their velocity. Looking back at the example of me and Angelo colliding, if I were to simply stand still and Angelo were to push into me, I would gain velocity, therefore changing my initial velocity, v1, from 0 to a new value, v1 prime.
Inelastic collisions have the same basic premise. There's two objects interacting with each other and have some sort of change of speed. If by some means a block ran at full force into another block, and let's suppose that superglue was on both sides, would we consider those two blocks as one entity? Now in real life, not necessarily, as they're still two entities, but in physics, we would actually consider them as one. They're combined. Therefore, if nothing really bounces from each other like in an elastic collision, something must be compensated in order to maintain momentum. And that something is mass. Let's look at inelastic collisions from a mathematical standpoint. Now instead of m1 v1 prime, m1 v1 plus m2 v2 equals m1 v1 prime plus m2 v2 prime, we actually consider m1 and m2 as one body. Because these two bodies are together, they have the same mass, it's just combined. Thus the right side of the equation would only have one velocity, v prime. Now looking back at our equation, we can form up a new inelastic one. m1 v1 plus m2 v2 equals m1 plus m2 v prime. Remember Newton's cradle? When we have the two balls sticking together, this represents an elastic collision, without the superglue of course. But there's one more piece of this information: energy. In every inelastic collision, energy is lost. Therefore, in Newton's cradle, whenever it collides, some of its energy can get converted into sound or heat, decreasing the amount of kinetic energy there is in the system. And therefore, that's why we see the system of the Newton's cradle ever so slowly slowing down.
Looking at some random object move, hopefully you can give yourself some existential security to the fact that you now know that almost everything has momentum. And as always, thanks for watching.